Welcome to this comprehensive university lecture on parasitology. Today, we are going to explore a fascinating and notorious microscopic organism known as Giardia intestinalis. Whether you are a hiker drinking from a mountain stream or a public health engineer designing municipal water systems, understanding this parasite is absolutely essential. Let us dive in and uncover its secrets. To begin our journey, imagine you are on a beautiful, remote hiking trip. You find a crystal clear mountain stream and take a deep drink, thinking it is perfectly pure because it looks untouched by civilization. But a week later, you are suffering from severe stomach cramps, bloating, and explosive diarrhea. What you could not see in that pristine water were microscopic, tough little shells waiting patiently to be swallowed. This invisible threat is commonly called beaver fever, a tiny organism that acts like a microscopic squatter, setting up camp in your gut to steal your nutrients. Now that we know the severe symptoms it causes, let us look closely at the organism itself. Formally, this parasite is called Giardia intestinalis, though in medical literature, you might also hear it referred to as Giardia lamblia or Giardia duodenalis. It is a protozoan, which simply means it is a single-celled organism. Furthermore, it is classified as flagellated. This means it possesses tiny, whip-like tails that act like little outboard motors, allowing the parasite to swim around actively and navigate once it reaches a favorable environment inside the host. Understanding how it survives brings us to its two distinct life stages. Outside the body, it exists as a cyst. This is a hardy, dormant shell that can survive freezing temperatures and harsh environments, just waiting to be swallowed. Once ingested, the warm, acidic environment of the stomach breaks the cyst open. It then transforms into the trophozoite stage. This is the active feeding form that uses a special suction cup called an adhesive disc to attach itself firmly to the lining of your small intestine. Let us visualize this journey with a diagram. On the left, you see cysts floating in contaminated water. Following the arrows, these cysts are ingested by the human host. As they travel down into the digestive tract, a process called exsistation occurs, releasing the active trophozoites. These colonize the gut, causing the illness. Eventually, as they move through the digestive system, they undergo encystation, turning back into resilient cysts. Finally, they are excreted in feces, ready to contaminate new water sources and begin the cycle all over again. This resilient life cycle makes Giardia a massive challenge for public health. It is one of the most common causes of waterborne disease outbreaks worldwide. Because the cyst stage is so tough, standard chlorine treatments used in municipal water plants are often not enough to kill it. This is why engineers must design advanced physical filtration systems. By studying its unique biology, we can protect vulnerable populations, advise travelers, and help pharmacologists develop targeted drugs that destroy the parasite without harming the human host. To manage this public health risk, we must move from biology to mathematics. Scientists use the exponential dose-response model to predict how likely an infection is. The formula is P equals 1 minus E raised to the power of negative R times D. Here, P is the probability of becoming infected. The constant E is the base of the natural logarithm. The variable R is the infectivity parameter, representing how likely a single cyst is to survive. Finally, D is the dose, or the number of cysts swallowed. As the dose increases, the probability of infection rapidly approaches 100%. Now that we have our formula, let us see this with a concrete example. Imagine our hiker accidentally swallows a tiny dose of just 10 cysts. Scientific studies give Giardia an infectivity parameter of 0.02. We plug these into our model, multiplying 0.02 by 10 to get an exponent of negative 0.20. Evaluating the exponential part gives us 0.8187, which is the chance the immune system fights it off. Subtracting this from 1 gives our final answer. There is an 18.13% chance of infection from just 10 microscopic cysts. This formula we just used leads us to an important question for engineers. What is the median infectious dose? This is the exact number of cysts required to infect exactly 50% of the exposed population. To find this, we set our probability p to 0.50 and keep our infectivity parameter at 0.02. Our goal is to solve for the unknown dose, d. First, we isolate the exponential term by subtracting 1 from both sides and multiplying by -1. This leaves the exponential term cleanly on the left side. Continuing our derivation, we now need to bring the variable d down from the exponent. To do this, we apply the natural logarithm to both sides of the equation. Because the natural logarithm is the inverse function of the exponential base e, they cancel each other out on the left side. This leaves us with just negative 0.02 times d. On the right side, we calculate the natural logarithm of 0.50, which gives us approximately negative 0.693. The negative value makes perfect sense since we are taking the logarithm of a fraction. We are now at the final step of our derivation. To completely isolate the dose d, we divide both sides by negative 0.02. The negative signs cancel out, ensuring our physical number of cysts is positive. The division gives us 34.65. Since we cannot have a fraction of a cyst, we round this to 35. This proves mathematically that swallowing just 35 cysts gives a person a 50% chance of getting beaver fever. This incredibly low threshold highlights exactly why water treatment must be so rigorous. To wrap up our lecture, let us review the most important ideas. First, Giardia intestinalis is a highly adapted parasite that uses a resilient cyst stage to survive outside the host. Second, because these cysts resist standard chlorination, public health relies on advanced filtration to keep drinking water safe. Finally, by using the exponential dose-response model, we proved that even a microscopic dose carries a massive risk of infection. You now understand both the biology and the epidemiology of this fascinating pathogen. Great job following along.